Okay, the next talk is by Kfir Levy on the algorithm for variational inequalities.
Hi, so I'm Kfir, and this is a joint work with Francis Bach. So this work is about convex-concave zero-sum games. So in such games, we have an objective M, which is convex in U and concave in V. And we have two players, say the U player and the V player. And the objective of the U player is to minimize the objective given the worst case response of the V player. And the objective of the V player is to maximize the objective given the worst case response of the U player. So what is nice is that for such games, you can actually obtain this objective simultaneously for both of these players. And solutions that obtains these goals of the player simultaneously are called equilibria. So more formally, given a solution or a point U and V, we can define its duality gap to be the worst case response of the difference between the worst case response of the V player with respect to U minus the worst case response of the U player with respect to V. And it is well known that the duality gap is always non-negative. And actually what we're trying to find equilibria for which the duality gap is exactly 0. And actually we're satisfied with approximate equilibria in which the duality gap is, say, epsilon close to 0. So these games, or such games, are prevalent in machine learning. For example, we have boosting, we have GANs, and we have constraint optimization problems. So now let's talk about how to solve such games. So we make the standard assumption that we have an access to a noisy gradient oracle for the gradients of M. And now it is well known that if we have an access to such an oracle, so after T such queries, we can find a 1/square root of T approximation of the equilibrium in the general convex-concave case. And this can be done, for example, by applying OGD simultaneously for both the U and V players. But actually, if the objective is smooth, meaning that these gradients are Lifshitz continuous, we can obtain a faster rate of the smoothness L divided by T plus the variance of the gradients sigma divided by square root of T by using a more sophisticated method called the mirror Prox algorithm. And we will go back to this method later on. So the issue, also, I forgot to tell that these bounds are actually tight, known to be tight. So the issue with these methods is that in order to obtain these tight bounds, you have to know in advance whether the objective is smooth or not. And if the objective is smooth, you have to know the smoothness parameter L, and you have to know the variance of the gradients. So what we do in this work, we are actually coming up with a new method that is based on the mirror Prox algorithm that doesn't have to know in advance this smoothness and noise properties of the objective, but it still provides you with the optimal bounds up to some logarithmic factor. So now let's briefly discuss the structure that we have in such convex-concave games. And basically, we'll see that they have a structure that resembles the structure of convex optimization problems, which will give rise to convex optimization style methods, more or less. Okay, so we can define a new variable x, which is actually the concatenation of U and V. U and V are the parameters in this convex-concave game. And similarly, we can define x0 to be the concatenation of U0 and V0. And now with these definitions, we can actually define two new notions, a monotone operator F and a gap function delta. And the important thing is that, to keep in mind, is that the monotone operator is somehow the analog of gradients in the convex optimization setting, and the gap function is the analog of the suboptimality between x and x0 in the convex optimization setting. So we'll not get into the definitions, but what's important is that given these definitions, this relation holds, and this relation looks like the gradient inequality. So the gap between x and y is small equal than the monotone operator at x times x minus y. Okay, and this will give rise to the algorithm that we'll see next. And of course, our goal eventually is to bounce the duality gap of this min-max game, and the duality gap can be directly related to the gap function that we described here. So now we can, with this definition of the monotone operator, we can describe the Nemirovski algorithm of Nemirovski. So in this Nemirovski algorithm, what we do, we have two steps in each iteration. First, we start at yt minus 1. We take a gradient step to xt, and then we measure the gradient at xt. We're going back to yt minus 1, and then we take a gradient step from yt minus 1 using the gradient that we measured at xt. So now replace the word gradients with monotone operators, and that's the Nemirovski algorithm for convex-concave games. So as we said, using this Nemirovski algorithm, and if we know the smoothness and noise properties, and we encode them into the learning rate, into this eta t, then we get the optimal bounds. But again, these methods, we need these parameters. But what we do in our work, we actually come up with a different learning rate, a learning rate that doesn't know this smoothness and noise properties. And this learning rate looks as follows, and it's very similar to undergrad, right? If the z's were the norms of the gradients, then we would have exactly undergrad, but actually undergrad will not work in this case, and I'll explain why. So actually what we're doing, we're using this definition of the z's. So actually I just discovered that zt squared should be xt minus yt minus 1 square plus the other term divided by eta t squared, okay? And so actually in the unconstrained setting, if you don't have any constraints, then you get that zt squared is actually the gt squared plus mt squared. But if we're doing the projection, then these are somehow the projected versions of gt and mt of gt squared and mt squared. And this is important. This is crucial because what happens is that the intuition to using this z's is that as we approach the equilibrium, these z's are going to 0, which implies that the learning rate will go to a fixed value and will enable this fast convergence rates. But if we would just use the gradients, then the learning rate would, even if we approach the equilibrium, the learning rate will decay, and this will prevent us from obtaining this fast rate. So I'll quickly describe one idea in the analysis. So in the analysis, kind of standard analysis enables you to show that t times the duality gap can be lower bounded by this term. And now if you look at this term, it's very tempting to try and to take the learning rate to be 1 over the smoothness, 1 over L, and then you get rid of the first term. But the trouble is that we don't know the smoothness parameter, and one of the main ideas in the analysis is to split the sum up to a point where 1 over the learning rate is larger than twice the smoothness parameter. And if you massage it a bit and do enough algebra, then you get the result that we talked about. Okay, so basically that's it. Thank you. Also for stochastic case, yes. Can you raise your voice? I'm not sure I understand what you ask. We can talk about it later. The doubling trick, without knowing the smoothness. I didn't think about it. So you see, You can apply double click without knowing the smoothness. Okay, but you can adapt to also to the variance, to the. Okay, okay. I have to think about it. Okay. Thank you.
Okay, the